This is Arman, and I'm going to talk about the future today. And the future today, like that we have right now. Um, and it's about brain signals. But first, a little bit about me. I'm Arman. I come from Berlin, Germany. I work for a startup called UNU GmbH. We're building mobility solutions. We're building electric scooters, microservices, domain-driven design, etc. If you're interested in any of those, I encourage you to check out our webpage and job openings. I'm also pretty much active on open source. I have a lot of libraries that range from front-end engineering to back-end microservices, distributed systems, platform as a service, web APIs, doing music in the browser, anything you can name. I have a repo for it on GitHub. I'm also leading a software craftsmanship school called Lonja. That's a software engineering school for women because I think you can see here there's a huge gap in the gender equality thing, and we need to fix that. So we're doing the best we can. You are encouraged to check any of these things. All right, so the question is, what is the ultimate hack? Now, I come from Berlin. We have a meetup in Berlin that is called Hack and Tell, Berlin Hack and Tell. So hackers from around town gather every month at the end of the month and present their findings, present their latest hacks. And it's like a small competition, which means they pick the kind of the coolest hack, the best hack, and it's a very good way to show your skills. So I thought I should, join and then do some stuff there, because I have a lot of stale repositories on GitHub that are pretty much undervalued. So I joined once and then twice, and I won both of them. So I wanted to win it 3 times in a row. It's kind of like a World Cup. If you win it 3 times in a row, they give you the cup itself. So I thought I would get the trophy. They're giving out a trophy. But turns out that they didn't. But the question was, I need to win this for the 3rd time. I have to come up with the ultimate hack, that I have to do something that, that is at the top. And I came up with this idea of brain research and doing something with brain signals. Now, this is news from last year. Elon Musk created a new company called Neuralink to build a high-speed highway between your brain and a computer to translate your thoughts kind of into a computer system. And he was very optimistic. He's always optimistic about everything, about all his deadlines. So he said, this should be usable in like 8 to 10 years. And we should basically have a channel inside your brain. So we'll implant electrodes in your skull, and that will basically give out wireless readings from your brain, so you'll be able to communicate with your brain signals without even talking. Of course, this is a little bit of a stretch to achieve in like 10 years' time. At the same time, Facebook came up in their conference with a new initiative. They have a new section called Building 8, which builds on brain interfaces again. So this is actually from one of their conferences. Their VP of Engineering, Regina Dugan, took the stage and said, you can type directly from your brain. And they are not as optimistic as Elon Musk. Let's say they're a little bit more realistic. They said this will be a reality in like 20 years' time, but that they're working on it so that you can type directly from your brain. So this is kind of defined as the future. So you can do, in the future, you'll be able to type directly from your brain. Your thoughts will be kind of like translated into any language that anybody speaks. So you'll be able to communicate. This is what the top companies are working on. This is a funny picture from 8 years ago. This is me, and this is my assistant. I'm just kidding. She's my best friend. She was just helping me out with my studies. This is an EEG headset, EEG cap, that holds a lot of electrodes. And basically, this is the research that I'm going to talk about today. But this is a technology that is already existing, and it was existing 8 years ago. In fact, if you look at this tweet from 2010, maybe 8.5 years ago, I wrote this tweet only using my brain signals. So I just typed it into a computer, and then also sent the command to tweet about that. So this is already there as as historical evidence that this thing was achievable in 2010. Obviously, nothing comes without pain. This is, I don't know if you can see it. This is kind of a horrible picture. I'm sorry for that first. But there are a lot of holes on my head. They are the electrodes. Basically, I was wearing that cap for like 14 hours, 15 hours, because this is safe research. No animals has been hurt in this research. And also no humans, because, you know, if this is going to kill somebody, you shouldn't kill your friends. So I just tried everything on my own before I scaled it up to other people. But yeah, it requires actually a lot of research, but it was actually possible. So a little bit history about the history of EEG. This is one of the first recordings from 1924 from a researcher called Hans Berger. He's a German researcher. Unfortunately, the name is legit. It's not made up. I know it's a very generic German name, Hans Berger, but that's his real name. So he was an EEG researcher, a very well-known, established one. And he said, you know, I can record signals from the brain, real signals from the brain, and nobody believed him. They actually shunned him out. So, you know, they didn't believe his research. They couldn't replicate his research. So they said, you are a charlatan. We don't believe you anymore. And he kind of lost all his credibility until 10 years later, people could do the same research and came to the same conclusion that, yeah, actually, there are some signals, electrical signals coming from the brain, and you can read them. So this was how it was looking maybe like 90 years ago. And pretty much, you know, very, very low resolution. There is not much data in it. It's just that you can see some shifts in the electrical signals. This is how it looks now. Of course, we have a lot more technology and more bit depth and more resolution, so we can get a lot more quality data from the brain. So unfortunately, the more data we get, the more it looks like noise. It's pretty much noise. There are some useful information here, especially around here, this part that I'm going to talk about, and the rest is purely noise that we're not interested in. That's why this is a very hard problem of machine learning. But let me show you in real time how weird it is. So I'm going to run a Node project. Hopefully it will work. Let's see. This is an electrode application, Electron application. Yeah. Yes, of course, live demos never work, right? It was working literally the minute before I started talking. And let's see if we're going to be able to get this thing working. No. Anyway, I'm going to retry this in a little bit. Maybe it will decide to work again. Let's go back to the presentation. All right, so this is kind of black magic. How does it work? We have 100 billion neurons in our brain. It's a very, very large number. 100 billion is kind of the number of stars in our galaxy. It depends on the astronomer you ask, but it's from 100 billion to 400 billion. So it's a lot. I wouldn't even think that we had that many cells in our body, but we have that many neurons that are firing every second, every millisecond, and we're trying to get electrical data out of them. So some chemical reactions occur in the brain, exchange of potassium and sodium, and they create a potential difference, which is a fancy word for voltage. So this is called an action potential. Basically, whenever an action triggers in the brain between some neurons, there is an exchange of these different chemicals, and then we get a voltage. And this is what we can read out of the brain. But the funny thing is, since the electrodes have to be external and there are some devices on their own, we can have 500 of them, 200 of them on a skull, and which means per electrode you have like 400 million neurons. The data that you get per electrode is the aggregate data from 400 million neurons, which is basically nothing because they all cancel out. All those neurons are firing in wildly different, if you think of vectors, in wildly different directions, and the net sum is pretty much close to zero. That is why, in fact, when your brain is active, we cannot read much data, much information from it, because everybody is firing like crazy. But when you're sleeping, the amplitudes that we read, the voltage that we read from your brain is a little bit higher because your neurons are also kind of sleeping. They are in harmony, and therefore the average amounts to something. The thing is, of course, we can open the skull of a patient or a person, and we can do invasive operations and implant electrodes in their brains, but this is a very deadly operation. The governments don't allow that. So unfortunately, this research is pretty much stable for the last 8 years, where I dropped off, and we're never gonna get it in the next 10 years because again, the governments will not allow it. I guess Elon Musk has a thing for stuff that governments don't like autonomous driving and brain implants. But yeah, you have to be terminally ill for the government to let you have brain surgery for electrode implantation. And the biggest problem is we actually don't know how this thing works. Unfortunately, we don't have any information of which part of the brain is responsible for what. You may have seen some maps on the internet, some research about this thing, but it varies wildly from person to person, and the brain can rewire itself, which means if you take the portion that is responsible for speech from out of a person's skull, from brain, if you cut that piece out, that person can learn talking again. So unfortunately, we don't know how it works. We don't know how it reorganizes, and therefore we are very, very limited in assessing the information that is coming out of this. All right. Now the paradigm that I'm talking about is typing with your brain signals. All right, and it occurs due to some surprises that happen in your brain. This is called the oddball paradigm. So we are, and I'm going to show you a demo in a minute, but we are randomly flashing stuff, and we ask you to focus on something. And whenever we show that thing, you're like, oh yes, this is mine. This is what I want to type. And at that moment, your brain produces a special signal that's called the P300. Positive 300, and the name comes from the fact that that signal occurs 300 milliseconds after you see something on the screen that alerts you, that is surprising for you, and we make use of that. So we detect that signal, and we predict what letter that you want to type based on that signal. So the thing is, this research started in 1988, and the first research was like 2.3 letters per minute, which is very, very slow. But if you think of the fact that the target audience for this is people with locked-in syndromes, with ALS, who cannot move any muscles, who cannot communicate at all, even 3 letters per minute is something. It, of course, doesn't have to be letters. It can also be pictures or emoticons or whatever. So you can communicate full sentences with little choices. With emoji, I guess the newer generation is pretty much used to that, forming sentences. But yeah, we basically upgraded this research to 20 letters per minute that is on a running system. So like every 3 seconds, you're able to write a letter. But that only happens with, unfortunately, with research-grade hardware, which is very, very costly, like north of 30,000 euros per unit. And that's even the beginning level. So it's not accessible to people. There are ways to make it accessible, but unfortunately, we couldn't do that yet. This headset that you see on my head, it has 14 electrodes, which is very dummy, and it's basically a consumer grade stuff that doesn't always work, as you just saw. You know, it sometimes works, sometimes doesn't, and whenever it works, the data that you get from it it's not that, unfortunately, that high quality. So here is the demo. This is me with the same headset. Obviously, in this video recording, it works. I start the same application. There's a countdown, and then you see a matrix of letters. So from A to Z, and then the numbers. 36 items on the screen, 6x6 matrix. It's randomly flashing. I want to type hello here, so I'm focusing on the letter H. As this is a consumer-grade hardware, the quality is not that good of the signal, so that you have to wait a lot for the system to pick it up, but it picked up the first little letter, H. And then I'm focusing on the letter E, because I want to type hello again. The second letter is E. I'm focusing on E, and whenever E lights up, I'm counting it. 1, 2, 3, 4. And whenever I do that, again, there's this P300 signal in your brain, and the software picks it up, and the machine learning algorithms basically are trained for that, trained to pick that signal up. And that's basically how they figure out what letter that you want to type, because you're not interested in the other letters. So the letters flash 120 times. And most of the time, 80%, 90% of the time, the letters that you don't want to type are flashing, so we're not interested in those. Therefore, it's very rare that the ones that you want to type are flashing. And yeah, we just make out which one it is. Let's see. It's actually a very boring watch. I don't move here. I can't see it picked up the second letter. I cannot move because this thing, especially this headset, is susceptible to movement, muscle movement. Even if you move your jaw muscles, the signals get scrambled. So you have to sit still, very, very still, and just look straight ahead to the screen. And if you move any of your head muscles or anything, you basically will miss all your signals. So that was hell. And yeah. Are you bored yet? Sorry? I blink, yes. That's all right, because I eliminate the blinks. Like, that is something that you cannot prevent, right? You have to blink, because hopefully you're human. So we have special algorithms to remove the blinks from the signals, because a blink is detectable, and it's very easy to detect that, also from a machine learning perspective. So we just remove the blinks, or sometimes we just ignore the blinks and take other signals. Let's move to the end, maybe. Yeah, so I have the hello, and I'm very happy, of course, because this is kind of a hard task. But yeah, the beauty of this is all done in JavaScript. That's why I asked if anybody knew JavaScript. You unfortunately cannot do this in Ruby, because it doesn't give you the front end. But if you know JavaScript, you can do every piece of the stack. You can, I wrote the code that interacts with the headset in JavaScript. All the machine learning algorithms are in JavaScript. All the UI is in JavaScript. So if you know a single language, you can basically do brain research today. So how do you start? The code is as simple as this if you have this headset. I didn't customize it for other headsets. It reads really simple. Constant mind requires wits. And you then open your mind, and you read your mind to the console. Let me try it again, all right? Let me see if this thing will work. I think it won't, but no. Oh yes, it worked. See, it worked. All right, this is a command line application that I wrote that shows your brain signals in real time. It's a command line application because why not, right? Everybody would like to see their brain signals on their console. You know, this is mostly noise, again. And especially that I'm talking, I'm moving all the joints in my head, all my muscles, so it's picking up everything. But if I sit still, if I stop talking and then just blink, you will be able to make out the peaks of my blinks. So see, those two are the blinks. Let's do a 3 blink right now. Yeah, 1, 2, 3. 1, 2, 3, 4. Yeah, see, those are kind of, you can grab those. But the rest is pretty much noise, and that's where the signals are. Let's see the application. There you go. This is much nicer. This is also filtered really good. So this is a front-end application. And when I move my jaw, you see it goes wild. People think this is real brain signal, but no, they are coming from your muscles. So unfortunately, there's a lot of fraud about this thing, about brain signals. Those are just junk. They're just useless signals. You cannot do anything with them. But this is all available on GitHub, so you can basically pretty much download it and play with that. Again, this is an Electron application. You can build your own version on top. Anybody is using D3, the library for charting? D3. 1 weak hand there, 2. Yeah, this is basically a D3 app. It's very, very simple. What it does is that, you know, mind.read goes to D3 function that updates data. Let me see here. This is the code in Visual Studio Code. If I run it, you know, require widths, mind open, mind read. And yeah, basically this is just log to the console. It gives you, all right, you can stop. It's very taxing on the computer, of course. It gives you the battery, a counter so that you can keep where you are in your sequence, and then it gives you levels that are for different electrodes. It gives you levels and their contact quality. So contact quality is a huge issue. This is basically running on contact lens solution, which is a little bit salty. Do you know the taste of the contact lens solution? I mean, I tasted it because it's, I mean, that's something that you basically put to your eye, right? It should be safe for you. It's a little bit salty, and that salt increases its transmission of electrons, so that when you put it on the electrodes, it makes better contact with your skin. It also works if you're sweaty a lot, because that also includes a lot of salt. But salt is the key here. Obviously, in real research, we use some sticky gels. If you have ever done EKG, electrocardiography, or ECG, you'd know that. It basically sticks. I'm lucky. I don't have anything on my head, so I could stick stuff. It wouldn't bother me. But my friends had a very hard time in university, where they had to clean their hair 3 times after the experiment. But yeah, anyway, let's go back. So this is where you start. And then we have the brain monitor, as I already demonstrated. And the brain bits, these are all open source. All the machine learning algorithms inside there are custom made for this purpose. And I'm going to show you the actual code too. But the technology stack is, again, all the way up JavaScript. I'm using native C add-ons for the headsets because this basically is connected wirelessly to USB to my computer, and it doesn't have an API. So it is actually encrypted as well, the communication. So some nice people on GitHub um, reverse engineered it, let's say, the encryption protocol, so that the data is available. It's a C library, so I built native C modules, C bindings for Node.js, so that you can require native C libraries for this headset in Node.js. And then it's basically Node.js for processing that takes in the data. It has 128 samples per second, so you get these electrode readings every kind of like 7 milliseconds or something, so that your code has to be really fast. But apparently JavaScript is enough for that. 10 years ago, we were doing this with MATLAB and native C. Now the technology and the processors moved on so that this basically can work in your browser. I'm using Electron again as the user interface shell and Vue.js on the front end. Anybody using Vue.js? One person, two? Please don't be shy. Three. Vue.js, that's a very, very nice, cute library. I encourage you to learn that for front end. There is a very nice library called Brain.js that implements neural networks. You can use either Brain.js for machine learning and processing in the application, or I ported my own BLDA classifier, Bayesian linear discriminant analysis classifier. Actually, I didn't write that. That was written by someone else in MATLAB, and I converted that, translated that into JavaScript. Believe me, that's something nobody wants to do. You know, like 10 lines in MATLAB is like 1,000 lines in JavaScript, and it's all matrix multiplication and very, very weird mathematical stuff I had to revisit after 10 years. So that was very, very scary, but it worked. In the end, it's all implemented in JavaScript. Unfortunately, anybody knows what eigenvector, eigenfunction is? Yeah, a few people, right? It's non-deterministic. There are no right solutions for that. And apparently, the implementations in JavaScript just don't work or are very, very slow. So for that, I'm running a web server in MATLAB that listens to requests. It's a REST API in MATLAB. So, sorry? So we have changed the roles, right? Node.js is doing the machine learning, and MATLAB, which is for scientific calculations, is doing the web service part. It takes in an array of values and calculates the eigenvector. That's all it does, and then sends it back as an HTTP response. So whenever I'm getting analysis data, I send it to that MATLAB server, get the result back, and continue doing the rest of the processing in Node.js. Which was fun. So if you remember, I built this for that hack and tell. So the more you hack weird stuff, the better, obviously. But it worked in the end. So a little bit more technical details. So we have raw electrode data that is 14 bits. And then we group them per second. So I break them into 1 second epochs after each flash. So for each letter, I have a 1 second epoch. I filter out the unwanted frequencies, so only get the frequencies between 1 and 12. And this is a very novel algorithm, by the way, this flow over there. So yeah, you better take pictures. Just kidding. But yeah, this effectively works. And then there are some more technical terms, winds rising data, again, to keep out the unwanted data points in my data set. Then I normalize the data around 0 so that the sum of the data is kind of 0. The thing is, again, the contact quality changes so much in your brain that no two recordings are the same. So you are a single person that you're wearing the same headset, you record your brain signals in the morning, you keep the headset, in the afternoon you do another recording, the signals change. The amplitudes change, everything changes. If you move the electrodes a little bit, 1 centimeter, that's like 1 billion electrodes, 1 billion neurons. So it still changes. The data that you get from the electrode changes. Therefore, you have to kind of normalize them to a standard so that you can run it, feed it into a machine learning algorithm. Then, anybody knows Nyquist frequency? Yeah. So I get rid of everything above 12 hertz, which means I can get by with 24 samples per second. 24 samples is enough to display data in 12 hertz. So what I do is I get rid of all the unnecessary data points because they don't contain any frequency information. And then I do machine learning algorithms, Brain.js or the custom BLD algorithm that you can find again in the source code. But yeah, the result is basically what you just saw, typing with your brain signals. So the conclusion of all this thing is basically JavaScript is, yeah, it's very powerful, but people think that it's powerful enough to read and parse JSON APIs. It's not only that, it can actually parse your brain API as well. So you can, go out and be sassy about your JavaScript knowledge. You can crack the code of the brain. Like no one else can kind of do that. So it's available to JavaScript. I'm kind of a JavaScript fan, in case you didn't notice. So I took it on as a mission to prove to the world that JavaScript is not a toy language, that you can do scientific research with it. That's why I implemented this 2-year research in JavaScript. But that's the end of my talk. Thank you for listening to me. Thanks. Now, if you have any questions, we have like 8 minutes. We can discuss this thing. Please. All right, the microphone should go to that lady over there.
Sorry.
It costs like 800 euros. Please.
Yeah, it was very interesting. Thank you. I come from a scientific background, mainly psychoneurolinguistics. Do you think this would be like applicable to like boost up experiments on EEG for ERPs related to like linguistic phenomenon? Would it be the quality would be enough?
So, if I get the question correct, like, can you use EEG experiments for linguistic models?
No,
Will
that's
the quality
already
be
been
enough?
done, but it's often like in a lab and it's like very invasive.
Yeah.
Not like.
Yeah. That, unfortunately, I would say no. But that depends on how persistent you are, how determined you are. You can get it, obviously, with a lot of pain. But there's a reason for why this field is very slow. This is cumbersome. Like, it just doesn't work. It requires hours of training, hours of preparation, and it changes from one person to the other. So, like, even within the same person, you get different results. So, it's not that useful, in fact, for anything. Please, there was this. All right.
I'm actually curious on the classifier use. How do you how do you classify it? What kind of classes that you?
Let me see if I have it here. Oh yeah. This is what I'm doing. I'm trying to separate the black signals from the red signals.
Right.
The black one is a signal that includes this P300. Okay? After this is the 300 millisecond mark. After the 300 millisecond, there's a peak. And the red one doesn't.
Right.
But this is an average of like 10, 20 samples for each. Obviously, you get some valid data that looks like the red one. You get some invalid data that looks like the black one. So you have to aggregate a lot of samples and then get their average and then, run any machine learning algorithm that can separate this thing. So linear discriminant analysis works. You have 2 classes, but it doesn't work because this is probabilistic. That's why we have a Bayesian approach to make it a little bit more
Flexible.
Yeah, flexible, and that we don't overfit to training data.
Right. And just out of curiosity, one more. I'm sorry. What is the accuracy of the?
So that depends on the speed that you want to type, because again, this gives you a probabilistic result.
So it's on the fly, actually.
Yeah, it's
You're
on the
doing
fly.
machine learning on the fly.
Yeah, exactly.
Right.
the thing is, you can get 90% accuracy with like 20 letters per minute. At least that's the research that I published 8 years ago. Maybe people could do better nowadays, but if you want to do faster, you definitely can. But then it's a matter of luck if you get the right letters or not, and the accuracy drops basically to kind of like 60%, 50%, and then barely usable. Because if you make a mistake and you have to delete that to retype the same letter, it's just not fun.
That's interesting. Thank you very much.
Yeah. Please.
Hi. This is not specific for your talk, but you mentioned research is low because this dangerous stuff, government doesn't like it. But I'm sure they must have done something with mice or things like.
Yes.
So
we definitely get brain signals from mice, and we can implant electrodes on their brains. That's how we developed the technology. Obviously, we didn't do it on humans. But the thing is, you can only develop the technical aspect of it, not semantic aspect, because the brain signals are not meaningful. Unless you want to learn for muscle movement, because then you can force them to do some muscle movement, and then you can kind of build your algorithms around that. But for cognitive stuff like this, it just doesn't work. So yes, you can develop the electrode technology in mice. That's what people do, but not actually the processing thing. And that is where we lack. Any other questions?
According to same question, but a bit different way, what about training on childs or, not so mature people who read so many books to think about all that at the same time?
That's a very interesting point. Obviously, I'm doing this for a very long time, so I kind of lost my ability to do this experiment because, like, I don't focus on it anymore. I'm not surprised by the blinking letters anymore because I know that they're gonna blink and stuff. Therefore, it works the best on people who never used it before. The more you get used to it, there's a curve. You get better for some time, and then your performance drops, like mine. So you cannot use it for long periods of time. I haven't worked with children. I worked with some patients, real patients, who cannot communicate, and this kind of worked for them. So that was good. Real people in need can use this system, but then they have some involuntary muscle movement, like their heads jolt to the side, so they lose their eyesight. So it then obviously doesn't work because you have to focus and see every letter flashing. So it's very tricky business. That's why this thing will not be useful for maybe 40 years or something until we figure out a better way. People are looking into optical, IR, and MR, like magnetic, optical, and other means of reading data or signals out of the brain. But unfortunately, that's also very, very low resolution, very low quality. Again, because we have 400 billion, 100 billion neurons. Please.
Just a quick question. How fast can you flash the letters in front of a user?
That's a perfect question. This is one area of improvement. You can go as fast as each flash takes around 30 milliseconds, which is like you can have 60 kind of frames per second if you go to 15 millisecond flashes, white and black, which works for some people, but it requires further training. So when people first use this, we start with a slow blinking system, and it doesn't work with this headset, for example, because this doesn't get the signals that fast. So it's a very, very tricky thing. But in our research, we optimize it to 75 milliseconds for each flash. That's how you get basically 20 letters per minute, which is 1 letter per 3 seconds, because you have to repeat this a lot of times. Like you have to count this 10 times to make sure that we get the right signal. So it's an area of research if we can get this faster, or modulate this so that some parts are faster, some parts are slower. It's a lot of research about this. All right, we are out of time, so I'll be around if you want to discuss this topic more. My head hurts a lot. Thanks for coming today. See you.